Hi there, we are from Group 19 and welcome to your Jacobi method lesson. This quick video will help you make the most of it. Let's get started. There are two assumptions made on Jacobi method. The first assumption is the system given A11x1 plus A12x2 plus A1nxn equals to B1 A21x1 plus A22x2 plus A2nxn equals to B2 an1x1 plus an2x2 plus annxn equal to bn has a unique solution. The second assumption is that the coefficient matrix A has no zeros on its main diagonal, namely A11, A22 until A and n are non-zeros.
Now let's look at the main idea of the Jacobi iteration. Firstly, from the system we solve the first equation for x1, second equation for x2, and so on to obtain the rewritten equations as follows. And then we make an initial guess if it is not given in the question. After that, we substitute the initial guess value into the right hand side of the rewritten equation to get the first iterations. Therefore, one iteration is completed. We repeated the same way to find the second iteration by substituting the x value of the first iteration into the right hand side of the rewritten equations. Last but not least, by repeated iterations, we form a sequence of approximations. In order to have the convergent solution, we have to ensure that matrix from the system is strictly diagonally dominant. An n times n matrix A is strictly diagonally dominant if the absolute value of each entry on the main diagonal is greater than the sum of the absolute values of the other entries in the same row. For example, the first matrix A is strictly diagonally dominant since the diagonal elements are greater than the sum of absolute value of other elements in row. While for second matrix A is not diagonally dominant since the absolute value of other elements in second row is greater than 6.
Consider the system and carry 3 iterations of the Jacobi method. Given the system 3x plus y minus z equals to 4, 2x plus 4y plus z equals to 1, negative x plus 2y plus 5z equal to 1. Okay, let's look at the solution. Given matrix A, 3, 1, negative 1, 2, 4, 1, negative 1, 2, 5. As we can see, matrix A is strictly diagonally dominant because the diagonal elements 3, 4, 5 as highlighted in the matrix is greater than the sum of absolute value of other elements in row. From the system, solve the first equation for x, second equation for y, and third equation for z to obtain the rewritten equations. X equals to 4 minus y minus z over 3, y equals to 1 minus z minus 2x over 4, z equals to 1 plus x minus 2y over 5. Since the initial guess value is not given, then we assume the initial guess value x, y, and z equals to 0. For the first iteration, we substitute the value of 0 into the equation and get the new value of x, y, and z. For the second iteration, we substitute the value from the first iteration into the equation and get the new value of x, y, and z. Then, to get the third iteration, we use the same method as for the second iteration, which we substitute the value from the second iteration x, y, and z into the equation, and we get the new value of x, y, and z. Then, as in the table, we fill in the value of x, y, and z for the first, second, and the third iteration, where for the first iteration, the value of x is 1.333. For the second iteration, the value of x 1.3167. For the third iteration, 1.6111. And for the y value for the first iteration, 0.25. For the second iteration, negative 0.4667. For the third iteration, negative 0.5. For the first z value for the first iteration, 0.2. For the second iteration, 0.3667. For the third iteration, 0.65.
Consider the problem of a steady heat conduction problem in a large brick plate with a uniform heat generation, with the boundary temperatures of TA and TB is given by 100 degrees Celsius and 400 degrees Celsius respectively. Determine the discrete nodal temperatures across the brick plate using the Jacobi iteration method. There are 4 equations given in these questions. The first one is 3000 T1 equals to 1000 T2 plus 2000 TA plus 2500. Second equation is 2000 T2 equals 1000 T1 plus 1000 T3 plus 2500. Third equation, 2000 T3 equals 1000 T2 plus 1000 T4 plus 2500. And last equation is 3000 T4 equals 1000 T3 plus 2000 TB plus 2500. And the initial guess is T1 equals to T2 equals to T3 equals to T4 equals to 100. By substituting the boundary temperature TA and TB into the equations, then we rearrange the equations to obtain T1, T2, T3 and T4. We will get T1 equals to 0.333 T2 plus 67.5, T2 equals to 0.5 T1 plus 0.5 T3 plus 1.25, T3 equals to 0.5 T2 plus 0.5 T4 plus 1.25, and T4 equals to 0.333 T3 plus 267.5. By substituting the initial guess value T1 equals to T2 equals to T3 equals to T4 equals to 100, we will get the first iteration of the nodal temperatures. T1 equals to 100.8, T2 equals to 101.25, T3 equals to 101.25, and T4 equals to 300.8. After we get the first iteration's values, we substitute back the values of T1, T2, T3 and T4 into the system of equations. And then the second iteration yields T1 equals to 101.2, T2 equals to 102.3, T3 equals to 202.3 and T4 equals to 300.2. And then we repeated the same way of the iterative process up to 10 and 20 iterations, and then the nodal temperatures up to 10 iterations, we get T1 equals to 135.2, T2 equals to 207.9, T3 equals to 282.2, T4 equals to 360.5. While if we do the iteration until 20 iterations, we get T1 equals to 139.7, T2 equals to 217.1, T3 equals to 292, and T4 we get 364.7. Lastly, we compare the nodal temperature of 10 iterations and 20 iterations with the exact temperature. We can say that the nodal temperatures after 20 iterations are edging closer towards the exact nodal temperature values.